Okay, consider one more problem. It is second order chemical reaction. So, consider the chemical reaction. You have a substance A and substance B, and they enter into chemical reaction, one molecule of A and one molecule of B, and the result is one molecule of C. To describe this reaction, we have some mass of A, some mass of B, and some mass of C. A and B are their masses decrease, and mass of C increase. The total mass A plus B plus C remains constant. Now, qualitatively, this reaction goes until one of these substances will be over. Yeah? Say you take one substance in excess and the other in deficit. So after this substance which is in deficit will be completely used, then the reaction stops. And we can anticipate that as we approach this situation, then the rate of reaction will go to zero. So it is just asymptotically we reach this situation. Now, my goal is to describe the mass of A, B, and C as functions of time. To describe it, the natural way is to measure the mass not in grams, but in moles. What is mole? Mole is the mass of a compound. Yes, we have some compound which consists of molecules. So we take the number of grams of compound equal numerically to its molecular weight. Yes? So, for example, the 1 mole of hydrogen, molecules of hydrogen at a normal temperature have molecular weight 2. So 1 mole of hydrogen is 2 grams of hydrogen. 1 mole of, say, oxygen, molecular oxygen, it's 2 atoms each has atomic mass 16, so the molecular mass is 32. So 1 molecule of oxygen is 32 gram of oxygen. And so on. We can say 1 mole of uranium-235, yes, is 235 grams of uranium. And the main property of mole is the following. 1 mole of any substance contains one and the same number of molecules, which is called Avogadro. clear from the definition that if the molecules becomes heavier, then proportionally grows the mass of these molecules. So we have the number of molecules is the same. And in this reaction, suppose we have 1 molecule of 1 mole of A and 1 mole of B. So the number of molecules here and number of molecules here is are equal. And so it is possible for, and eventually they all get into reaction, and we have 1 mole of C. Yes? And this is the most natural way how to describe the relative masses of the substances as they get into reaction. So therefore we will measure the quantity of A, B and C not in grams but in moles. Yeah? So and call them molar mass. So how many moles of A, B and C are in our disposal? No, say in these are some substances dissolved in water. So this solution contains some number of moles of A, B and C. Let's introduce notation. X molar mass of A, Y molar mass of B, and Z molar mass of C. Yes? And now we want to find X of T, Y of T, Z of T. No, we know X of 0 equals X0, Y of 0 equals Y0, and let us take Z of 0 equals 0. So we started from a situation when we have only A and B, and Z will be formed in the course of reaction. No, if Z is not 0, we simply subtract the respective numbers of so C does not take part in the reaction. So we simply may forget about the C which was by the beginning of reaction and consider only the new C which is forming in the course of reaction. And now, as I said, for any mole of format C, we have to spend 1 mole of A and 1 mole of B. So we take 1 molecule of A, 1 molecule of B, put them together, and they together form 1 molecule of C. And this means that Z of T, X of T equals X0 minus Z of T. So you have to, if you form Z of T molecules of C, then we have to spend the same number, Z of T, of moles of A, so which is reflected here. And Y of T equals Y0 minus Z of T. And therefore we can express, if you know initial masses of x of A and B, we can express mass at every moment of A and B just in terms of Z. And the main law of reaction is the following. dz dt equals k times x of t times y of t. So the rate of formation of C from A and B is proportional to the present molar mass, or simply physical mass, but better to molar mass of A and the present molar mass of B. Yeah. So we have this equation. So now I can substitute here, eliminate here x and y, use these formulas, and have this equation. dz dt equals k x0 minus z, y0 minus z. K is a constant specific for this reaction. Yes. No, it depends on different things. For example, depends on the volume of our vessel where reaction is going. So the larger the volume, the less the concentration. So for smaller concentration, the reaction goes slower. It depends on the temperature, depends on, I don't know, on all the situations or the circumstances of chemistry. So, but if you consider only dependence on x and y, it is just a constant. It is constant of reaction. Now we can solve this equation. Let us try to solve this equation. So dz, it is autonomous equation. X minus z, x0 minus z, y0 minus z equals, say, k dt. Integral dz x0 minus z, y0 minus z equals k t minus t0, as usual. And now initial condition. Here for this equation, let me z of 0 equals 0. So we started from no C is absent initially. If C is present, then this present C does not affect reaction, so we simply ignore it. So we take this. We'll use this initial condition when we will find this constant C0. So now, okay, again we decompose this integrand into the elementary fraction. So 1 divided by x0 minus z, y0 minus z equals p x0 minus z plus q y0 minus z. So we write it, it is equal p y0 minus z plus q x0 minus z divided by the same, this denominator, equals now p y0 plus q x0 plus minus pz minus qz, p plus qz divided by the same denominator, and that should be equal 1 divided by this denominator. So we have the equations p plus q equals 0, this coefficient at z, p y0 plus q at 0 equals 1. So q equals minus p. P y0 minus x0 equals 1. P equals 1 y0 minus x0. Q equals 1 x0 minus y0. Yeah. Yeah. And now, integral dz x0 minus z y0 minus z equals integral p x0 minus z plus q y0 minus z dz equals, no, p, I know in this, but for now I write this. First of all, x0 minus z is positive. Yes, because we start from 0 equals 0, and anyway, x0 and y0 are numbers of molecules of A and B, and they numbers of molecules at the time t, and they cannot be negative. So both this and this positive. So this means that I can integrate it. It is logarithm minus p logarithm x0 minus z minus q logarithm y0 minus z equals logarithm x0 minus z to the p minus p y0 minus z minus q. Logarithm of this. Uh, Now we return here. So 1 of p plus q is 0, and p is 1 over y0 minus x0. And q equals logarithm of say q is, okay, let us write x0 minus z divided by y0 minus z to the power 1 x0 minus y0. Yeah. Because minus p is q, q is this, 1 x0, yes. Yes, minus p is q, minus q is p. Yeah. Whew. Okay. And this is the left-hand side, this integral. And so let us return here. Logarithm of x0 minus z, y0 minus z to the power 1 x0 minus y0 equals k t minus t0. Now it remains to find t0. For this, let us take t equals 0. For t equals 0, z equals 0. So we have logarithm x0 minus z equals 0, x0 over y0, all this to the power 1 over x0 minus y0 equals t equals 0 minus k t0. One moment. So it is 1 over x0 minus y0 logarithm x0 over y0 equals minus k t0. logarithm x0 y0 equals x0 minus y0 minus k x0 minus y0 t0. Okay, so from here we find t0. t0 equals minus logarithm x0 over y0 divided by k x0 minus y0 equals logarithm of y0 minus logarithm of x0 k x0 minus y0. Yeah. So we have this solution, and t0 is here. Oh my God. Now we have to find z from here. Z. So let me write now the full formula. Logarithm of this equals this. So x0 minus one over x0 minus y0 logarithm x0 minus z y0 minus z equal k t minus t0. No, we know t0, it is here. Let me not write it here at this moment. So logarithm x0 minus z y0 minus z equals k x0 minus y0 t minus t0. X0 minus z y0 minus z equals e to the power k x0 minus z t minus t0. Oh, great. x0 minus y0. Okay. Uh, so from this, we know what is T0. We can find a final answer. Okay. So let us look here. One moment. Let me finish this. Zero, yes. So we have to substitute here T0. T0 is here. E minus k x 0 minus x0 minus z y0 minus z equals e to k x0 minus y0 t e minus k x0 minus y0 t0. T0 is here, so here this is in the denominator, equals e k x0 minus y0 t, e minus k logarithm y0 minus logarithm x0 divided by k x0 minus y0, and here e minus k x0 minus y0 times logarithm y0 minus logarithm x0 divided by k x0 minus y0. It is in the exponent. So this and this cancels, equals e to the power k x0 minus y0 t. E to the power, this cancels this, logarithm x0 minus logarithm y0 equals, it is equal to x0 divided by y0 e to the power k x0 minus y0 t. And let me denote all this as A. I don't want to repeat it. And so we have the following: x0 minus z y0 minus z equals a. x0 minus z equals a, y0 minus z. Z equals a minus 1 equals a by 0 minus x0. Yeah? A by 0 minus x0. Z equals a y0 minus x0 divided by a minus 1. And now let us substitute here a. Z equals a y0, it is x0, this times y0, it is x0, e to the power k x0 minus y0 t minus x0 divided by a minus 1 x0 y0 e k x0 minus y0 t minus 1. Let me write it like this. X0 is common factor here. Here it is not. Whew. This is the answer. Now, I wanted to see what will happen if, say, x0 is more than 1 0. So x0 is the number of moles of A, y0 number of moles of B, the initial moment. So if x0 more than y0, then I want to find the limit of this when x0 is more than 1 0. Then x0 minus y0 is positive, so this exponent is growing. Exponent is growing, so this 1 becomes negligible related to this x0, and here 1 is negligible to compare, this 1 is negligible compared to this as well. So we can forget about this, and then it looks like e to the power k x0 minus y0 t and x0 is positive, so it is positive, yes? And here is x0 divided by y0, e k x0 minus y0 t. Now we can cancel this and this. x0 divided by x0 y0, it is y0. So, is it realistic? Yes, it is, because if x0 more than y0, then the first will be exhausted the compound B. Yes, because initially we have less modulus of B than of A. And so, as soon as y0 is exhausted, and they are exhausted in the same rate, so the number of moles which were lost by A at any moment compared to the initial state is equal to the number of moles lost by B. Yes, and this means that after all the molecules of B are used, the reaction stops because remains only A and it cannot produce C. So the number of molecules of C is equal to number of moles is equal to Y0. And next, what happens in opposite case? If x0 less than y0, what will happen? Then this x0 minus y0, x0 minus y0 less than 0, and e to the power k x0 minus y0 t goes to 0 as t goes to infinity. Yes? So in this case, z, what is the limit of z? In this case, this term will go to 0, so it is negligible, and this term will go to 0. So remains minus x0, it is here, remains only this goes to 0, and here remains, this goes to 0 because this term, this factor goes, and remains only minus 1. So x0 less than y0, so as soon as all the molecules of x0 are used, reaction stops, and the number of molecules of C is equal to initial number of molecules of x0. And we recovered it from this relatively simple solution. But I have to acknowledge that this solution, whatever is not so, I cannot say that it is very complicated, but it is a little long. Know what to do. It is typical when you work with differential equations. Okay, so let us finish with this. And next we consider some other nonlinear models. For now, let's finish. Have a good time. Bye.